The next sensor that we're going to discuss is encoder. When we have an optical encoder, we can detect the angular position of a rotary device. Normally, if we have an optical encoder, we should be able to equip this kind of sensor at the joint of a robotic arm or at the wheel of a mobile robots. The structure of optical encoder is straightforward. We got the light source on one side, and on the plate, this is something sometimes we call it encoder disc, and it's going to have slots. Um, so the light is going to when it's going to go through when it's open. It's going to be blocked when the slot is not cut off. Most of the time, we have two rings with slots. They are 90-degree difference between each other. So in this case, we should be able to detect the direction of the angular movement when it starts to rotate. On the other side is going to be a photodetector. So when the photodetector detect the signal, it's going to be turned up. So the signal is going to be a sequence which includes on and off signals. For incremental type encoder, it's straightforward. Again, we got emitter on one side, we got receiver on the other side. So when we have this kind of configuration, it is going to generate signal. Either it's going to be on or off, depending on whether it's going to be the slot is going to be blocked or not. Also, we are going to have two channels. One is channel A and the other one is channel B. By looking at the configuration over here, you're going to find the distance of the phase is going to be 1/4 cycle, or it's going to be 90 degrees. Okay, so depending on where the position or the sequence between A and B, we should be able to detect whether it's 90 degree or 180 degree or 270 degree or 360 degree. So instead of just having on and off signals, we can actually generate 4 different status for this kind of incremental encoder. But keep in mind, when we are dealing with this kind of encoder, lines is an important property that is going to determine our resolution. So what is a definition of line? Let's start from something simple. If I got a disk and I tell you it's only one line, which means it's going to be one slot. So the slot is going to be half of the disk, which means the receiver is going to be turned on when it rotates to this side. So one slot is going to have two conditions. One is on, the other one is off. So the output is going to be something like this for the full cycle, 0, 360 degrees. So it's either on or off. If we have, this is one line. If we have two lines, it means that we're going to have one over here, the other one is going to be slot. One over here, the other one is going to be slot. So in this case, when we have two lines, it doesn't mean we have only on and off two status. Instead, we're going to have, let me put in more detail. It's going to be on when it's over here, off when it's over here. It's going to be on and off. 1, 2, 3, and 4. And over here, this is my 360 degree. So with this one display over here, we know that a single line is going to determine two status, on and off. Let me do a more detail over here. So this time, if we have 4 lines instead of 2, we draw 1, 2, 3, and 4 lines. So when we start to generate the on-off signals, we are going to have on, off, on, off, on, off, on, and off, which means we're going to have a status for a 4-line encoder disk. So the resolution over here is going to be 2 pi divided by 8. So each one, the resolution is going to be pi over 4. So keep that in mind. If we are using those kind of things, the line is going to determine how much resolution we're going to have for this specific encoder. So this is one type, and incremental encoder is one of the most popular type of encoder used in industry. That is one thing. The other thing is, okay, we talk about if we have channel A and channel B, then it's going to be a 90-degree difference. So if we put that into our configuration, what do we have? So let's say we have 2 lines. 2 lines is going to be here, and the other one is going to be this one. Okay, so we're going to have those 2 off. So on the other side, we're going to have this one off and this one off. Okay, what does that mean? Okay, we got 2 channels, so what? So if we draw those kind of things accordingly, you're going to find interesting fact. So this is my 0 degree, this is going to be my, this is one sequence. So it's going to be 1, 0, and this one is going to be 1, 1. This one over here is going to be 0, 1, and this one is going to be 0, 0. So if it's just one channel, you only have 1 and 0, 2 kinds of status. But if you have 2 channels, you actually have 1, 0, 1, 1, 0, 1, and 0, 0. Instead of just 1 and 0, you can always see something like this is going to be only have 1 and 0. But if you have 2 channels with 90-degree phase difference, we are increase the resolution from 1 count to 2 counts. So the resolution, in other words, is going to be doubled. So 2 channel is going to give us the benefit, even though the fabrication technique does not need to be improved. But with 90-degree difference, we're going to have the resolution doubled, which is fantastic. What's better is if we know it's going to be 1, 0, 1, 1, 0, 1, 0, 0, this sequence, it means that it's going to be rotated in one direction. If the sequence starts from 0, 0, and 0, 1, and 1, 1, and 1, 0, we know it's going to be moving in reverse direction. You cannot use the encoder disk with only one channel to detect the rotating direction. However, if you are having 2 channels, then we can use this advantage to determine the rotating direction of my shaft. So this can be a very good application without using an additional sensor to detect the rotating direction. With encoder itself, we should be able to tell which direction the motor is rotating. The other thing is, in addition to channel A and channel B, sometimes we get another channel, we call it channel Z. Channel Z, in this case, let me change the color so you will know which one I'm talking about. So from this one over here, you might notice that I got the small slot over here. This is my channel Z. So Since we only have one slot at, in channel Z, it means that every time if you see this one being turned on or the on signal has been sent from your encoder circuit, it means that it has returned to a specific location. Normally, we can use this one as our 0 degree, or going to be our 180 degree, or even use this one as our calibration index. Every time, if you want to return to its initial position, we probably want to set this channel over here to be my 0 degree. So everything starts from there. And by counting corresponding number of counts from channel A or channel B, we can determine the absolute position compared to the index. So that can be a very good tool for optical encoder. Another type is instead of using incremental encoder, sometimes we might want to use absolute encoder, which means we are having, depending on how many bits we are going to talk about. In this case, we got 1, 2, 3, 4, 5, 6, 7, and 8. This is going to be 8 bits. Okay, so this kind of 8 bits, this 8 bits encoder, you're going to have 2 to 8, 256 positions, because every time this is binary, so every time you got your signal, it's going to read a channel simultaneously. So it's going to be either one or on or off reading from each channel. And for the A receivers, we can determine the position directly without counting on the Z index, because the information is good enough. Since at every location, the combination is going to give us a different binary number. So without knowing the index, we can still determine what is my current position. And this one is more precise than the incremental encoder. However, this one sometimes can be more expensive than incremental encoder. But obviously, this can be a more precise sensor that we can use for robotic device. This is another configuration for absolute encoder. So when we are using absolute encoder, it means that the binary code or gray code has been set. There is no two positions that is going to share the same code from absolute encoder. If you receive this specific number, it means that it's unique for this specific encoder. So keep in mind when you are using absolute encoder, all the angular positions has been determined at the shift. Okay, let's work on one of the example. This example is a 2.5 long vane is rotated slowly in a circle. The motor and gears attached to the vane at its center, it is necessary to know the position of the vane within 2 cm. So what must be the resolution of the optical encoder attached to a shaft of the position shown? Okay, so this one over here is pretty straightforward. I have a vane. And on the other side, I want to know the revolution movement. That is going to be 2 cm around this circle. So this part over here is 2.5 meter. For the diameter. So before we can actually do anything, we would need to know the resolution. desired resolution for this thing because we talk about 2 centimeter around around the circle. So with this 2 centimeter, how do we determine the required resolution? So let's define what are given and what we need to find. We are given that the length is, or the diameter is 2.5 meter. And we need to have resolution 2 centimeter. And we're going to put an encoder over here to detect the angular movement. So how much noise we're looking for? So how much noise of the attached encoder? First, even though this is a 2 centimeter, we need to know what is delta theta. So delta theta is simple. We're going to have 0.02 meter divided by pi multiplied by 2.5. This one is resolution, so the unit over here is not pi, it's going to be a revolution. If you do the calculation, you're going to find this number equals to 2.547 multiplied by 10 to the power of -3 revolution. So every 2 centimeter detection is going to be corresponding to this amount of revolution in the system. So with this one set over here, the next thing we need to do is to determine how much lines, because we know that for one line we can actually have two status. One is on, the other one is off, which means if I don't know the number of lines, I'll have n lines encoder. N is some variable I just assume for the number of lines in the encoder we're going to attach on the shaft. So 2.547 multiplied by 10 to the power of -2 revolution equals to 1 over n, because this is revolution divided by line. One revolution include this n lines, and also this is not the end. We need to multiply that by 1/2 line, because one status is going to cost you not one line but 1/2 line, since we have on and off status. So it's going to be 1/2 line instead of a full line. So if you do the calculation, you're going to find your n is going to be 196.35 lines. Well, that's great because we got our answer. The question I have for you is, can you use n equals to 196.35 lines? The answer is no, because we cannot make 0.35 lines. Every line we make is going to be integer. You cannot say I have 0.2 lines because physically it's not feasible. So instead of using this one over here, we're going to say the required number of lines is going to be 197 lines per revolution. But another condition is that 197 lines is not available for any encoder nowadays because the number is kind of weird. So instead of using 197 lines, you probably can order something which is 200 lines. Okay, so this is how we use the existing information to calculate the required resolution of our encoder attached to a specific shaft we want to design roboted on that.